Okay, we are now entering Unit 3. This is Unit 3.1, Plate Tectonics and Ocean Floor, where we're going to actually talk about the history of the idea of these moving plates, even though they weren't called plates at this time. If you take a look, we have an ocean floor that is not flat. Up until probably World War II, maybe World War I, people actually thought that water would have actually eroded anything that stuck up, so the ocean floor was as flat as a pancake. Of course, as flat as a pancake on a spherical object. But we now know that we do have islands that are volcanoes reaching from the bottom of the ocean. We have trenches, which are the deepest places in the ocean. We have a Midocean Ridge, a Mid-Atlantic Ridge, which is the one down the middle of the Atlantic Ocean, tend to be in the middle of the ocean. Sometimes we have trenches on both sides. When we have trenches, we have volcanism. It's called a volcanic arc if it's actually on a continent. It's called an island arc if they're out in the middle of the ocean. They can become mature island arcs in the case of like the Philippines or Japan. If a lot of volcanoes grow together and we get a pretty good sized island. And we now think that it's actually powered by this convection that's down here. Caused by convection cells. Heating of the mantle and hotter areas actually making material rise, and then convection pulling these two plates apart. Molten rock melting through the slab and actually punching through, creating brand new oceanic rock, and on the opposite end, the destruction of oceanic rock. So what happened? World War II actually gave us the idea of a non-flat ocean, like I said before. And after World War II, when we were looking for submarines, we actually discovered this Midocean Ridge, which is 46,000 miles long. It runs down the middle of most of the oceans. It's wider in some areas and narrower in some areas, and we'll talk about why we think that's true. Some places it actually sticks up like in Iceland. And we also have the deep ocean trenches, which pretty much ring the Pacific Ocean, which gives you an idea why this is called the Ring of Fire. I thought these were going to come in as animations, but plate tectonics actually starts with a thin ridge, rigid plate. It's hard as a rock that creates the surface of the Earth. Plates move. They can move toward each other, they can move away from each other, or they can slide past each other. Three ways that almost anything can move in relation to another object. And plate motions create major geologic features such as deep ocean trenches, deep sea trenches, mountain ranges on continents as well as in the ocean, and volcanoes. Here is a picture of all the Earth's earthquakes, and you can take a look and see they run down the middle of the oceans, that 46,000 mile long mid-ocean ridge. They also are very intense where the plates are coming together. Sometimes it's in an ocean where we have two oceanic plates. Sometimes it's actually where an oceanic plate hits a continental plate, and sometimes it's actually where two continental plates hit. But this doesn't give you an idea of the depth of earthquakes, and we find all three depths, shallow, intermediate, and deep, where we get the plates running together, where we find pretty much shallow with some shallow intermediate earthquakes where we actually have plates being ripped apart. So if you take a look, these things very well mark the idea of the plates moving. Where some plates, like that plate right there, the Juan de Fuca plate, this plate right here, which is the Nazca plate, they probably have short lives because South America is moving this way. North America has moved and pretty much covered the Juan de Fuca plate. The whole idea comes about Alfred Wegener. Back in the early 1900s, the earliest 20th century, he started looking at maps, and at this point maps actually started to get good enough that we could actually start seeing the shape of continents, and he started looking at these continents as though they actually fit together. North America and Europe and Asia, North America and Africa, South America and Africa. We can put India, which you normally think as being up here, down close to here, Antarctica and Australia, and even Madagascar is in there. And then we notice we have a huge ocean, and then around 250 million years ago, the Atlantic Ocean opened up, and that was the death of the Pacific Ocean. This is called Panthalasia. Alfred Bullard, 1960, which is 40 years later, when we actually started getting the maps, actually realized that if we look at the continental margin, which is the part of the continent that's underwater, would actually fit better than just the shape of the continent that's above water. And if you take a look at this, we'll talk about these guys later, but there's some evidence on these continents like tropical forest fossilized results actually being showing that the world was by the, or excuse me, this part of North America were by the tropics, the equator, as well as this area down by the pole, South Pole, completely covered with glaciation. The theory of continental drift, Wegener's going to actually use a couple of different things that are pretty easy to see to actually talk about continental drift. Continental drift is the idea that the continents drift. They're not being pushed or pulled or powered in any way. They just drift. And the first one was the foot of the continents. And again, that's best if we use the continental margins. Fossils, we look at some of these fossils. This is a fossil that was about the size of a dog. Same with this one. This fossil is actually found in South America and Africa, and they started to find these fossils. Now they're 4,000 miles apart, but how could the critter have been here, walked all along North America, all along over to Asia if there were land bridges, and then down through Africa and not be found fossils anywhere else? This is a crocodilosaur, right here, which is Mesosaurus, which is again found in South America and Africa. Crocodiles will go out into the ocean, but they're not going to swim across 4,000 miles, and it wouldn't be just one. If it was like a storm-related thing, it got blown across, it'd have to be a pretty good population. We also have plants, and if you take a look at these plants, I could imagine it in South America, I could imagine it in Africa, although it's kind of dry in those locations. I can imagine it in Madagascar and India, but I can't imagine it in Antarctica or maybe Australia, as dry as Australia is. So it looks like these guys were not where they are today. And then we have glacier irregularities. If we take a look at glaciers, we actually think glaciers form if they form on land, they're going to move in towards the ocean because that's downhill. So they should be moving out of India. And what is India doing with glaciers? And what's Africa doing with glaciers? And this part of South America, not the mountains on the west coast. And Australia, what are they doing with glaciers? And I can actually imagine that Antarctica has glaciers. So if you actually move these guys around, put North America and Asia, or Soviet Union, Russia, real close to the equator, these guys are actually forced to go down into the southern deep latitudes where we'd find a lot of ices. And then geologic likenesses, we have mountains that are on the east coast of the United States, which are similar to the west coast of Africa and also into Europe. We have rock similarities that are actually found down in lots of locations. So it looks like these guys actually were found different places at different times. Okay, so the map. Talk about glaciation. Glaciers are going the wrong direction, and they're actually in places where they shouldn't be today. Tropical Laurasia flora. If we take a look at this area of the United States, which has pretty good coal, and that area of Europe, these guys show evidence of being tropical, not subtropical they are today. Polar Gondwana flora, where we actually find flora excuse me. We find flora where we shouldn't find it today, and then coral assemblage, where we actually find coral in rock that's either in desert or it's high above sea level, where it actually was underwater at some point. Okay, direction of glaciation movement. So glaciers are moving, actually showing that ice was now in temperate regions. Other climate evidence, differences in climates at different latitudes, and land fossils.